OK, so with those 5 questions answered, we're basically done with designing DNS. You've seen, once again, in English, how everything gets passed back and forth. We saw that you use signatures to ensure integrity on records, and you use certificates to pass trust down the tree. By signing someone else's public key, you say that you trust them. So that's basically it for the high-level design. And just like we did with regular DNS, we'll now spend a bunch of time thinking about how someone would implement this in code. So it gets a little bit messier here. The design is pretty beautiful. Now it's going to get a little bit in the weeds, but it's an interesting exercise to see how someone would implement this in code. So here are the ideas we've already seen to summarize how the DNSSEC design works. The first big idea was we'll sign our records. And the idea is that the name server with the private key can generate signatures, and nobody else can make signatures that are valid. And everybody else can verify those signatures using the name server's public key. This will help us stop network attackers because man-in-the-middle, on-path, or off-path attackers have no way to change that signature without being detected. They don't know how to generate their own signature for a malicious record. So this stops people from tampering with records, whether they're network attackers or maybe even the recursive resolver itself, if it was hacked. And signatures have another great benefit that we haven't talked about, which is that they provide object security. So remember we said that there's a difference between securing the channel and securing the object? Well, with the signature, you can keep the signature around for as long as you want, and it provides security on the object itself. In other words, when you cache the record, you can cache the signature as well. So wherever this record goes, whether it's in your cache, or whether it's going across the network, or whether you're sending it to someone else, as long as it always comes attached with the signature, you can verify the integrity at any time that you want. So we've changed from securing channels to securing the object itself. That's another benefit that we get from using signatures. And the second idea that we used was public key infrastructure, or certificates. So we'll use the same tree that we've always been using in DNS, and the way that we delegate trust is by using a certificate. If you're the parent, say you're root, you will sign your child's public key. So for example, root will sign the .edu name server's public key. And that's basically a statement saying, I'm root, you trust me, and I'm signing the public key of .edu. So therefore, if you trust me, now you should trust them too. I'm signing a statement saying that they are trustworthy as well. So this is how you delegate trust from the parent to the children. And at the very top of the tree, we have the root name server. Remember, with certificates, because you're signing other people's public key to spread trust to them, the trust has to start from somewhere. And in DNSSEC, the trust starts from the root name server. And the way that we encode trust from the root name server is to hard code their public key into all the resolvers. So everybody knows the root name server's public key, and they know that if you verify something with that public key and it checks out, you know it's trustworthy and it's good. So this public key is just a piece of information that everyone knows. It's not something that an attacker can tamper with because it's a piece of information that is very well known. It's like the planet that we're on. So this is great because this defeats some of the problems we talked about. If a malicious name server wants to tamper with a record or provide a bad signature, well, we're going to assume that the malicious name server will not have been trusted by their parent. So this is something you kind of have to assume. But with certificates, you're only going to pass on trust to people that you trust because of some real life or business relationship. So it should be the case that if you were a .edu name server, you're not going to go and sign the key of an attacker and say, this attacker's key is trustworthy. You wouldn't do that because in real life, you know they're an attacker or they haven't given you their trust. So it should be the case that using some sort of real life trust verification, the only people who get valid certificates that get trust passed on to them are legitimate, untampered name servers. So this should hopefully help us defeat malicious name servers. because each name server will only delegate trust to people that they actually trust are legitimate and not malicious. So this is our second big idea, and by putting these two ideas together, you get DNSSEC.